go through the key for lesson 9. Number 1, I'm going to leave to you guys. You can tell pretty straightforward what's happening from the key, I think, if you look at it closely. Number 2 might have been a little bit trickier because you need to what you need to do first is find acceleration. So if you look back at the question, I'll give you more context. It says a ball traveling at 50 meters per second begins rolling up an inclined plane before coming to rest. The ball comes to rest to a stop 80 meters up the incline. What was the velocity of the ball that far after starting up the incline? So what we have to do for that one is we know VI. VF, it says it comes to a stop. And we know the distance there too, right? So we know VI, we know VF, we know the distance. What we're going to be able to do from those three things is figure out acceleration first. And that's what you do in part 1. You'd figure out the acceleration because the acceleration is going to be the same on this ramp the whole time. So if you figure out the acceleration anywhere, you know it for part 2. Oh, my writing's getting terrible. Part 2. Okay. And then now that we know the velocity, or the acceleration, sorry, was negative 15.6, all we have to do then is solve for VF using that velocity now and our same VI, if that made sense, hopefully. Okay, it ends up being positive 10.9 meters per second, so up the ramp. So number 3 is going to be pretty much identical to the practice problem that I did in the last video. So I'm going to skip that one and let you guys look through the answer here to see if you maybe missed like a negative sign on the display on the distance there or something. Or maybe you got it right. Okay, number 4 you might have found a little bit tricky. So number 4 says an object is allowed to free fall from rest for 6 seconds. What distance does the object travel in the last second of the fall? So if this is like a meter stick or something, I've kind of gotten drawn here. And let's say we drop an object. It's going to drop, but remember, since it's accelerating downward, it's not going to cover very much distance to begin with, but then it's going to cover more and more distance quicker and quicker as it goes down, right? And we want to know how much does it cover, how much distance does it cover just in the last second. So pretty much, I don't know, in the first second, maybe it covers like that much. In the second, it would cover like, that much. And then third, the arrow you can see is getting like longer and longer every time. It would be something like that, right? Really what we got to do is just figure out how far did it fall in 5 seconds. So this is the ball. What we do is figure, okay, it fell that far in 5 seconds. So what I'd do is figure out for part 1, I'd say D is equal to VIT plus 1/2 AT squared. And VI, remember, it starts at 0 because we're dropping it, so that goes away. So for the first one, so for D, I'm going to put D5 for D5 seconds. That's going to be equal to 1/2 times negative 9.81 meters per second squared times the time of 5 seconds squared. All right, so the distance, D5, would end up being negative 122.625 meters. Okay, so that's the distance it would drop for that. But then we're going to say, okay, it's going to drop, maybe we'll do a different color here, in the 6th second. In 6 seconds, this thing would have dropped like this far. And what we're really after, so is the distance here from there to there. That's the distance that dropped within that last second. So what we're going to do is now is just figure out the distance, the orange one here. How far, make it orange again. D6 would be equal to 1/2 times negative 9.81 meters per second squared times 6 seconds squared. So D6 would be equal to 176.58 meters. Sorry. Okay, so we just got those two numbers. Oh, and negative. Really, all we got to do is figure out what's the difference between them. So if you figure out the distance between these two numbers, so just subtract them, you would end up with this number here. This method here, this is right, right? Like all they've done here is just went like, okay, the same type of thing. So in the end here, we just went d6 minus d5, right? But this method, we just put the formula for d6, which is right here, right? That's just this. We put that there. And then d5, the formula for d5, we put, which is, that. We just put that there. And then just all we did was factor out 1/2 a out of that. That's what happened here. So if you remember to your math with factoring stuff, and then we're able to just put those numbers in and you get the same number. But really the big concept, if you don't want to do it all like, the math kind of more intensive math way like that, you would just go d6 minus d5. Just find d6 to find d5 and then subtract them. And that's kind of what I did over here. All right, let's carry on to 5. So number 5 says a car accelerates uniformly from rest at a rate of 2 meters per second squared for 6 seconds. So that's accelerating, right? It then maintains a constant speed, so not accelerating, for 0.5 minutes. Finally, the brakes are applied and the vehicle slows down at a uniform rate and comes to rest at 5 seconds. So it decelerates or it slows down for the last part. Find the maximum speed of the car and the total displacement. So if you look at what I've got here is I've got a picture of kind of what happened, right? So this thing, if this is a velocity time graph, right? This is velocity on the y-axis, time along the bottom. Then on the velocity time graph, a straight line like that means it's a constant acceleration, or it's accelerating, right? A flat line means it's moving at constant velocity, and then going down, it's accelerating again, but it's negative acceleration. So first off, it was saying what's the final velocity, right? It wants to know what the maximum speed is. It's really saying what's this speed, right? Because that's going to be our maximum. So it gets up to its maximum speed after part 1. So what we got to do for that one, well, actually first I'm going to show you down here too that I've written everything we know. So V1 was 0, V2, that's what we're looking for. We don't know what that is. And then distance, we don't know, like D1 or any of the Ds. Time was 6 seconds, and then acceleration was 2 meters per second squared. All right, so this is kind of part number 1 here. It said, what's its maximum speed? This is the formula that I used here, just rearranging. V is equal to V2 plus V1 over T. And then solving, it's 12 meters per second. Okay, and then part 1, I know the initial velocity, the time, so we just solved by just plugging everything into this, and D1 was equal to 36. D2, this is kind of the reason why we even have this question on here, is because we use these equations, right? These ones that have like the acceleration. All these ones here, right? A, like acceleration there. All the ones with distance over here, those were all acceleration. The only formula we have on your formula sheet that's for constant motion, so not accelerating, is this one. So as soon as it says that it's not accelerating or it's constant velocity, that's the only one you're going to use. So we need to use that one for the middle part. So we go back, yeah. So that's why here we use D is equal to V times T. So V times T, and figured out that that's what D2 was. And then the last part we had to use a different formula because we don't know actually what the acceleration was on that part of the graph. But we do know that the velocity here is the same as the velocity that we just found. So VI in this case is going to be the same up here. It's 12. So we're going to have 12 plus 0 because V2 is going to be 0, right? It comes to a stop. Divide by 2, and then that all happened within 5 seconds. So then D3 is equal to 30. And then over here, we just need to add them all up. I've got 36 plus 360 plus 30 is equal to 4.3 times 10 to the 2 meters. It's number 9. I keep doing this. Lesson 9 is what I keep seeing that. Number 5. This is a car. Oh, no. Sorry, number 6. While driving her car, Mrs. Jones sees an obstruction in the road. It takes her 0.8 seconds to react and put her foot on the brake. Her car is traveling at 25 meters per second. How far will the car travel before she puts her foot on the brake? All right. So the key bit here, when she is traveling in her car, I got my amazing car drawn here. We can think about it as coasting, right? So as she wants to stop, before she puts her foot on the brake, this thing is going to be going at constant velocity. So we need to use our formula right here. That's the only one that we can use, right? Because that's constant velocity formula. They're not slowing down yet. We're just coasting. So that's the one we got to use for the first one. So that's just going to be 25 meters per second times 0.8 seconds. Our distance is 20 meters that they're going to travel. That she's going to travel before she hits the brakes. Now for part two, so draw like another car because I'm so good at drawing cars. It's the same car, I swear. Okay, so now at this point though, let's say that they hit the brake, right? So now you're actually going to start slowing down, and it tells us for part B that the acceleration is 9.3, and it's going to be negative 9.3. We're going to call this way negative, right? Like we've been doing. So it's decelerating, or it's going to be a negative acceleration. V1 was how fast they were going. So initially they were going 25 meters per second. V2, we know that she's going to come to a stop. So she's going to go this way and then come to a stop. So VF is equal to 0. Distance is what we're looking for. So now we just need to choose the right formula. And again, if you wanted to, you could look and say, okay, time is nowhere in our equation. So I chose the formula that didn't involve time or even care about time. So if you do that, we just got to plug everything in. Remember the negative 9.3. You get 34 meters in that case. So then for the total distance, it's going to be part A and part B just added together to get 54 meters. Number 7 says a stone is thrown straight down from the top of a cliff with an initial speed of 6 meters per second. It reaches the bottom in 3 seconds. How high is the cliff? So we look at 7 here. We can see, okay, thrown down, so it's going to be negative 6. Tells us the time. It tells us the acceleration. So now we just really need to figure out what the distance is, and it ends up being negative because it's below you. And just remember that even though you're throwing it down, you might think that it should have like a bigger acceleration. It doesn't. It has the same acceleration. The rate that the speed is changing or that the velocity is changing is the same. So number 8 says a ball is thrown vertically upward from a window at 10 meters per second. It hits the ground 5 seconds later. What was the height of the window from the ground? So like I said before when we were kind of looking at these ones, someone might think, like if this was my window, I guess right here, that since we threw it up and then down again, if I find like my distance, that you might think that it's the distance from there all the way to the ground, right? But it's not. It's just the distance from where I started to the ground. So exactly what I'm looking for in this question. So as long as you keep your negatives and your positives straight in this, you'll end up with the right answer. So positive 10 meters per second. 5 seconds. Acceleration is still negative 9.81. If you put that into this formula, and if you want to figure out how I got that, or you could remember that VF was nowhere to be found in that question, and I wasn't trying to find it, so this equation doesn't even have VF in it. Plug all your stuff in, you get negative 72.6 meters, because that's the change in distance, or the distance from where I started to where I ended. Okay, number 9, I'm going to let you guys go ahead and try that one on your own. Yeah, it's a bonus question, a little bit more difficult. If you want to give it a try, great. If you're not quite up to it, don't feel too bad. And I'm going to end that video there.